All right, welcome back for your next lecture for Physics 235. This is week 11, day 2, scheduled for release on April 1st. And today we're going to be discussing RLC circuits and transformers. Note that this is a slight change from the original syllabus policy, as I mentioned on Monday, and up here in the corner you can see today's lecture is going to focus on sections 15.3 and 15.6 from volume 2 of your digital textbook. So, most of what we're going to talk about today is RLC circuits, and then later we're going to spend a little time talking about transformers. So, an RLC circuit, and we're specifically going to be looking at an AC RLC circuit, will consist of an AC power supply connected to a resistor, R, an inductor, L, and a capacitor, C. So that circuit might look something like this, where this is the battery whose voltage as a function of time is capital V naught times sine of omega t. This up here at the top is the resistor with resistance R. This is the inductor with inductance L and the capacitor with capacitance C. And we are going to analyze the behavior of this circuit mostly using Phasor diagrams. So one thing to note here is recalling back to what we talked about on Monday, that the current in these circuits is not always in phase with the power supply, meaning that the current does not always reach its peak at the same time that the voltage across the battery does. When we talked about resistors, the current through a circuit that's just an AC power supply and a resistor, the current was in phase with the power supply. Then we talked a little bit about inductors and capacitors in AC circuits. And with the capacitor, we found that the current peaked before the voltage across the capacitor. And with the inductor-only circuit, we found that the current peaked after the voltage across the inductor. So we have no reason to expect that the current will be in phase with the battery voltage, and we really have no idea how far out of phase the two might be. So we're just going to have to assign that a variable. So what we're going to do here is we're going to define a new quantity that specifies how far out of phase the current will be, and we'll eventually learn how to solve for it. So we are going to specify a variable called phi, which is known as the phase angle. And this is very similar to the phase shifts we talked about earlier in the course. And the phase angle is going to tell us how far out of phase the current is with the battery voltage. This means that we can write the current in the circuit, current as a function of time, as the maximum value for the current, I naught, times sine of omega t. Well, if it were just sine of omega t, then the current would be in phase with the battery voltage, because both of them would be sine of omega t. And what we're going to do here to represent this unknown phase shift in the current is we're going to subtract our phase angle inside of the argument for this sine function. Note that current will be the same for all of our circuit elements because they are all in series. So, a good thing to do next is to try to figure out what the values for VR, VL, and VC are, because all of our standard rules for circuits about voltage and current still applies to this circuit. So all of the voltage from the battery must still be spent in the following form. The voltage of the battery, which is little v as a function of t, is going to be equal to the sum of the instantaneous voltage at that specific moment in time for each of our resistor, inductor, and capacitor. So we're going to need expressions for the voltage across the resistor as a function of time, the voltage across the inductor as a function of time, and the voltage across the capacitor as a function of time. And it will turn out that this is not too difficult to find. We are going to have a sine of omega t in each of these, but note that each of these circuit elements will have some maximum value of the voltage across it and some minimum value of the voltage across it. And we can draw this in a phasor diagram. As a reminder, a phasor diagram represents various things that oscillate in an AC circuit: the current, the voltage. So it might be good to start by drawing the current. So let's represent the current in this circuit with the vector I naught, where I naught is the maximum value of the current, and then the y component of this vector gives you the value of a current at a specific moment in time. So as everything in this diagram rotates around at an angular speed of omega, the y component of that I naught vector will change, and that y component is the current in the circuit. Well, for resistors, we know that resistors are in phase with the current in the circuit. So our vector for the resistor voltage, this is VR, is going to be pointing the same direction as our current vector. And just like before, with everything on a phasor diagram, the y component gives you the value of the resistance at that specific moment in time. Since this is all rotating at a rate of omega, that means we can label this angle right here. And this angle right here, since it's the angle to the current, is not just omega t, it's the argument of the sine function for the current that I'm moving my cursor around up here. This angle is omega t minus our phase shift phi. Then we can start to draw arrows on this phasor diagram for our other circuit elements, other than the resistor. As we know from the Eli portion of our Eli the Iceman mnemonic, Eli says the EMF peaks before the current for an inductor, which means that the EMF for our inductor is going to pass the y-axis before the current. So just like our phasor diagrams from our previous sections, the arrow for capital V of L, the maximum voltage across the inductor, will point here, 90 degrees in front of the current. And as with all phasor diagrams, the y component of this vector will give you the value of the voltage across that element, the inductor, at a specific moment in time. And as we know from the ice portion of our Eli the Iceman mnemonic, for a capacitor, the current peaks before the EMF across that capacitor, which means that our capacitor voltage will be down here. Let me draw that arrow actually just a little bit shorter for reasons that'll become apparent later. So this will be the maximum voltage across the capacitor, capital VC, and as always, the y component is the voltage across the capacitor at that specific moment in time. And everything here continues to rotate around the central point, and again, the angle between the capacitor voltage and the resistor voltage is 90 degrees. So at some point here, we are going to need to know the values for each of these vectors. We need a way to find I naught, VR, VL, and VC. And it will turn out some of these formulas are fairly straightforward. We already have a good idea for VR from Ohm's law. The voltage across the resistor is just going to be, the maximum voltage across the resistor is going to be the maximum current times the resistance. And now we're going to see the benefit of the reactances, both capacitive and inductive, that we introduced last time. Because the maximum voltage across the inductor is also just going to be I naught times the inductive reactance. And the maximum voltage across the capacitor is going to be I naught times the capacitive reactance. So we have very similar formulas here with our capacitive and inductive reactances taking the place of our resistance for those particular circuit elements. So it will turn out that we can find all of the values that we need to find in order to analyze this circuit. And I want to show you how we're going to do so. But first, I want to just kind of state the results. You can find each of these in the following way. And I'm going to have to clear off this page to make some more room here. So give me just a second here. So the formulas that you would eventually find here are, you can find the phase angle phi by taking the inverse tangent of the following expression. The voltage across the inductor minus the voltage across the capacitor over the voltage across the resistor, all of those being maximum voltages, which, if you look at these purple formulas over here, each of these terms inside that inverse tangent contains an I naught that you can cancel out, so we can rewrite the formula for phi as the inverse tangent of the inductive reactance minus the capacitive reactance over the resistance. And you can also figure out the formula for I naught, because I naught is going to equal the maximum battery voltage divided by something called Z, where Z is a new quantity we are introducing called the impedance, which has units of ohms. Think of the impedance like the equivalent resistance for an AC circuit. And you can see that it follows a similar form here, where the maximum battery voltage would equal the maximum current times the impedance. So you can kind of see where it's taking the place for resistance here. And the formula for Z is as follows. The square root of R squared plus X sub C minus X sub L, quantity squared, all of that underneath the square root. So in terms of major formulas for an RLC circuit, should focus on these, should focus on the current in the circuit, and you should focus on the fact that we still have to spend the entire battery voltage. Now, I want to give you a way to think through these formulas and why it should make sense that these are the formulas. And to do that, I'm going to draw another phasor diagram. So let's get the diagram drawn to begin with. And there's going to be quite a few vectors on this diagram. One of the things we're going to do here is note that the maximum voltage, the battery voltage, or V naught here, is going to be the vector sum of all of our individual vectors. So I can write this out mathematically down below, that our battery voltage vector V naught will have to equal the vectors for VR, VL, and VC all added together. These are the maximum values for each of those because I'm using that capital V. So we can find a way to draw this in a helpful manner if we remember that, well, our V sub R is perpendicular to both V sub L and V sub C. So we can think of these VR, VL, and VC a lot like components of the vector V naught. So the only problem right now is that we have three of them. So let's combine VL and VC into one vector by subtracting the two of them. So that means we might have our V sub R vector, capital V of R, the maximum resistor voltage, pointing this way. And then at a right angle to that, we have another vector that is VL minus VC. This is why I made the VC vector shorter, just so it's clear that this vector would point up and left, not down and right. So this has now accounted for each of our three voltages across our circuit elements, at least the maximum voltages across them. And now we said that these vectors act like components of our vector V naught. So we can finish out this parallelogram here. and see what direction V0 must point for this particular circuit. And here, V0 has to point this direction. Again, just following this formula down here that these vectors have to add up to give you the total vector. So now let's label a couple of these angles to help make things a little more clear. This is a right angle, not a very good label, I'll make a better one, between V sub r and VL minus VC. And we already said that the angle between V sub r and the x-axis here was omega t minus phi. But the angle up to V0 is still the same omega t that it was before, so that must mean the angle between V0 and V sub r is phi. So hopefully you can see some of the triangles we're dealing with here that helped us find these formulas for phi. So I will outline one of these triangles in yellow real quick. We're working with this triangle right here. And if we take the inverse tangent of this angle, we need opposite over adjacent. And the opposite side is over here, which is the same side as this side. It's VL minus VC. That's the opposite side to that angle phi. And then the adjacent side is just V sub r right here. And that's how we can get this angle phi from this formula right there. So depending on whether VL minus VC is positive or VL minus VC is negative, we might have the voltage for the battery peaking before the voltage for the resistor, or we might have the voltage for the battery peaking after the voltage for the resistor. Phi can be either positive or negative, and we'll talk a little bit more about that when we do the upcoming example. So this is the general idea behind AC RLC circuits and how we might represent these things as phasor diagrams. And now I want to do an actual example with numbers because this is can be a little bit of an opaque concept without an actual example. So we're now going to make ourselves an example, and I am going to set it up as follows. So we have an AC power supply over here on the left that has a maximum amplitude of 1 volt and is going to oscillate at 200 hertz. Connected in series to a 4 ohm resistor, a 3 millihenry inductor, and an 800 microfarad capacitor, and we want to analyze this circuit. Which means we're going to need to find the values for I0 and eventually formulas for the voltage across each of these elements as a function of time. And in order to do this, a great place to start is to try to find the impedance. So the impedance Z, finding the impedance here is a lot like finding the equivalent resistance of a resistor circuit. It's one of the first steps we have to take here. So Z is the square root of R squared minus quantity x sub L minus x sub C squared, all under the square root. And we have the resistance, but we don't know our value for our capacitive and inductive reactances yet, so we're going to need to find those first. So we have a formula for our inductive reactance is omega times L, where omega is in radians per second, so we need 2 pi times frequency f in hertz times L instead, which means that's 2 pi times 200 hertz times the 3 millihenries, or in scientific notation, 3 times 10 to the negative 3 henries worth of inductance. And that gives you a inductive reactance of 3.77 ohms. We can do the same thing for the capacitive reactance, which is 1 over omega C. Following that same pattern of replacing omega with 2 pi times the frequency in hertz, we get the following expression. 1 over 2 pi times 200 hertz times the capacitance, which is 800 times 10 to the negative 6th farads. And when you calculate this all out, you get a value of 0.995 ohms. So now we can plug in to our formula for impedance and see what we get. We have 4 ohms as the resistance, and then the difference between these two reactances, 3.77 ohms minus 0.995 ohms, all in parentheses, that squared, all under the square root. And we, once we plug this into our calculators, get a value of 4.87 ohms for our impedance, which is a great first step in this problem. Because now that we have the impedance, we can use our modified form of Ohm's law for an AC circuit, that V naught, the maximum value of the voltage applied to the circuit, equals I naught, the maximum value of the current in the circuit, times the impedance. So the maximum value of our voltage applied to the circuit is 0.1 volts. It's the maximum voltage of the battery. And we don't know I naught yet, but we do know that Z is 4.87 ohms. So here we can solve for I naught and get a value of 0.0205 amps for our maximum current in our circuit. Now from here, eventually we're going to need the angle phi. And we have a formula for the angle phi as the inverse tangent of the inductive reactance minus the capacitive reactance over the resistance. And plugging in some numbers here, that gives you the inverse tangent of the difference between those two ends up being 2.77 ohms divided by 4 ohms for the resistance. And we get a value for phi that is 0.607. And note that this is in units of radians. I put my calculator in radians for this calculation, and it's expected that all of these values inside our sine and cosine functions are in radians. So just a brief note about what it means for phi to be a positive number specifically. When phi is positive, it means that the inductive reactance is greater than the capacitive reactance, which means the battery voltage peaks before the resistor voltage. And the reverse is also true. When phi is negative, that means the inductive reactance is smaller than the capacitive reactance, and the battery voltage will peak after the resistor voltage. So with our situation the way it is here, with a positive value for the phase, we know that our battery voltage will be peaking before our resistor voltage, which if you look back to that last phasor diagram we drew on the previous page, you can see that the V naught vector is placed counterclockwise from VR, which as this whole assembly of vectors rotates at the rate omega, that means V naught is going to pass over the y-axis before VR. So we already expected this bit about the battery voltage peaking before VR, and now we can tie that to whether phi is positive or negative. So from here, we now need to be able to find the current in the circuit or the voltage across any of our circuit elements at any point in time, and I will give you some formulas to do so. First, let's talk about the battery. We know that the voltage across the battery as a function of time, which was why I'm using the lowercase v here, is going to be V naught times sine of omega t. This is determined by the battery or by the AC power supply itself, and nothing can change this. Current, on the other hand, current will be the same for all of our circuit elements, so I only need to have one formula for the current. And that formula, as we mentioned before, is I naught times sine of omega t minus phi. Or in our problem, we have a positive phi, but other problems might have a negative phi. then we need to look at each of our circuit elements individually. For the resistor, well, we know that Ohm's law still applies, so we can say the voltage across the resistor as a function of time is going to equal the current as a function of time times the resistance. So this becomes I naught times capital R times sine of omega t minus phi. Note that this term right here, I naught times R, that is just capital V sub R. So capital V sub R is the vector that rotates on our phasor diagram, and this sine of omega t minus phi defines its rotation, and then the gives you the y component of that vector, or the value at any given point in time. Now for the capacitor, we know that Q equals Vc, so the charge on the capacitor as a function of time equals the voltage on the capacitor as a function of time times the capacitance. From this, we need to actually end up doing an integral if we want to solve for the voltage across the capacitor directly, because current is the derivative of the charge. But we can also just look at what we know, that the voltage across the capacitor will equal some maximum voltage, which we know is equal to I naught times the capacitive reactance. And there will be some oscillation of the voltage across the capacitor at the same rate of omega t minus phi. But don't forget that the capacitor voltage was phase shifted relative to the voltage of the battery to begin with, so we still keep that same plus pi over 2 in our capacitor formula. So this is the formula for the voltage across the capacitor at any moment in time, where this term here, the coefficient, is just V sub c. And last but not least, we can look at the inductor. And we had a formula for the voltage across the inductor as a function of time was negative L times the derivative of the current. Let's use the right one. Derivative of little I sub t dt. And by working through that derivative and then by converting the cosine that we get to a phase-shifted sine, we eventually get that the voltage across the inductor as a function of time is equal to I naught times x sub L times sine of, again, omega t minus phi, this time with a minus pi halves. And just like before, I naught times xl is just that vector capital V of L that we saw in our phasor diagram. So now you are equipped with all of the equations you could possibly need to determine any value of relevance in this circuit at any given point in time. You could determine the voltage across any circuit element at any point in time, inductor, capacitor, resistor, or battery, or the current in the circuit, which is the same for all circuit elements. And that's basically going to answer almost everything you'll need to know about this RLC circuit. There are some additional details about the power in such circuits and about something called resonance, which we're not going to have time to get to, but this is at least a good start and it will be appropriate for what we need it for in the course. So this is all I have about RLC circuits. So the next thing we're going to look at here is transformers. And I have a specific page for this. There we are. So now we're going to talk about transformers specifically. And transformers exist in power line circuits, at least, to adjust the voltage and current of an AC signal. And we can see how this works out in terms of power lines in the diagram that I have shown off to the right here. We start off at the power plant, and the power plant produces AC power at a voltage or a maximum voltage of 12 kilovolts. So these values that you're seeing are going to be all of the capital V0 values. But it's actually not a good idea to transmit power lines or electricity across power lines at the same voltage the entire time. We eventually end up stepping up this voltage to 400 kilovolts. Note that that is a lot higher than the 12 kilovolts that this started out at. Then eventually, our circuit gets stepped down in voltage down to 13 kilovolts, which is again V0. And then last but not least, when the power comes directly to your house, you have just a V0 of 240 volts. So what's happening between each of these stages is a transformer. So between the power plant and these high transmission voltage lines that you see running through the countryside, we have a transformer. And that transformer takes the voltage and raises it from 12 kilovolts to 400 kilovolts. And then later along the line, we have a step-down transformer, which brings the voltage from 400 kilovolts back down to 13 kilovolts. And then last but not least, we have one more transformer, a smaller one, that steps the voltage down even further from 13 kilovolts to the 240 volts that our houses are ready to accept. So these first two transformers, the step-up transformer and the step-down transformer substation, are usually large complexes, fenced off with a bunch of electrical-looking equipment, and there's a lot more going on there than just the transformer, but the most critical piece of electrical equipment in these setups is the transformer. And then the last step-down transformer, well, if you look at the top of power line poles, you'll see a little metal cylinder at the top of a lot of them, and that is the last step-down transformer before the power gets to your house. So before I show you the couple of very simple formulas for how transformers work, I want to talk a little bit about why we might want to transform the voltage here to begin with at all. And it comes down to the fact that no matter what transformers we send our AC signal through, the power is constant. And we didn't have time to really talk about this in detail because we skipped this section, but the power in an AC circuit is equal to still I times V, but these are the RMS values, meaning the peak values divided by the square root of 2. So every time we step up the voltage, we also step down the current, and that's for a very good reason, because all electricity that flows dissipates some voltage due to the resistance of the wires. And from the power company's point of view, every volt dissipated by the resistance of the wires is less electricity they're able to deliver to consumers and less money that they're able to make. So it is in the power company's best interests to lower VR as much as possible, the voltage dissipated due to resistance in the wires. They can do this in one of two ways. One of them is to lower the resistance of the wires. And these wires are generally already constructed of very low resistance materials, as low is as feasible. But what they also want to do is lower the current in the wires. So this is why power is transmitted over long distances at incredibly high voltages. Because if we step up the voltage, then we are in turn stepping down the current. So we have the highest current where we have the lowest voltage. We will have the highest current here when the power enters your house. And we will have the lowest current here in the high voltage transmission lines. So as this electricity travels across cities, counties, states to reach your house from the power plant, that long distance that it has to traverse is done at a very low current, which helps to minimize the amount of voltage dissipated by those wires. So now on to what an actual transformer looks like. And there are two halves of a transformer circuit called the primary and the secondary half. And they look as follows. The primary side of the circuit is hooked up to some AC power supply. For the figures above, this AC power supply is the power plant itself, generating electricity however it generates electricity. And at the end of this circuit, there is a coil of wire or an inductor. And this circuit will be very near to something called the secondary circuit, which looks as follows. So the secondary circuit also has its own coil of wire and is not connected to an AC power supply. The inductor in the secondary circuit is going to act as the battery for this secondary circuit, and there will be some inherent resistance in that secondary circuit in order to keep the current from becoming infinity. Most real-life inductors also have one other aspect to them that's going to be a little hard to draw, but I'm going to try. They have something called an iron core. So this that I've drawn here is supposed to be an iron core that goes through the center of each of these two coils of wire. What the iron core does is it helps to channel the magnetic field caused by each of these circuits, and that in turn increases the efficiency of the transformer. So more of the magnetic field generated by the primary coil will pass through the secondary coil, which means the largest induced EMF possible in the secondary coil. So there are a couple things you'll want to note about any given transformer. One of them is that the number of turns matters. Basically, how many loops each of these inductors makes. So the primary coil will have a number of loops that we'll call NP, N primary. And the secondary coil will have a number of coils equal to N sub S, the number of coils in the secondary circuit. If the number of turns in the primary coil is greater than the number of turns in the secondary coil, this means this will be a step-down transformer, meaning the voltage will decrease. And vice versa, if the number of turns in the primary coil is less than the number of turns in the secondary coil, this will be a step-up transformer, raising the voltage. And the number of turns in these inductors enter into our equations for the voltage across each of these circuits. And these equations are expressed as ratios. The maximum voltage in the secondary circuit divided by the maximum voltage in the primary circuit is equal to the number of turns in the secondary circuit divided by the number of turns in the primary circuit, which kind of helps you see what a step-down transformer does. It means your secondary voltage, your induced voltage, is smaller than your primary voltage, the external voltage, if you will. And a step-up transformer gives you a secondary voltage that is higher than the original voltage in the primary circuit. Last but not least, we also have a formula involving the current in these circuits. So the current in the secondary circuit at any given point in time divided by the current in the primary circuit at any given point in time is equal to the number of turns in the primary coil divided by the number of turns in the secondary coil. Note that these fractions are kind of opposite from each other. With the voltage formula, secondary is on the top for both the voltage and the number of turns. For the current, it's opposite. The primary number of turns is on the top of the fraction for that side of the equation, but on the lower side of the fraction, the denominator for the current. So this means when you have a step-down transformer, like we mentioned before, the voltage may go down, but the current in the secondary circuit is going to be greater than the current in the primary circuit. And for a step-up transformer, this means that as our voltage rises in the secondary circuit, our current in the secondary circuit will then be less than our current in the primary circuit. So this is the basis of transformers and basically what I want you to understand about them, which is the fundamental idea of how they work, the idea behind why we would want to use a transformer to raise or lower the voltage, and as well as the general equations for how voltage, current, and the number of turns are related to each other. Just a note as to this diagram down here, this part that I'm boxing in red right here, that is the transformer. Everything else is just the rest of the circuit. So it's just this part that is boxed in red is what is located at each of these locations in this diagram up here where we have a transformer. They might be arranged slightly differently in real life or have additional machinery or circuitry involved, but somewhere in there, there are two coils of wire that are connected by an iron core. So that is it for today. Thank you for watching, and have a good day.